pH of weak acids.
Hey everybody, back again for another video here. pH of weak acids is what we're going to look at in this one. In this problem we're going to look at the propanoic acid at equilibrium. So we're looking at all the conditions at equilibrium, and what we're going to do is we're going to try to figure out one, what is the concentration of all the species at equilibrium, and two, what is the pH, and then three, we're going to look at what is called percent dissociation. Okay, a couple things I probably should have included in here is the formula for propanoic acid, which is C3H5O2. Okay, so that's our formula for propanoic acid. And also, we need to know what the concentration is, and I forgot to type that in here, which is 0.100 molar. So we're going to put a 0.1 molar solution of propanoic acid into water, and we want to figure out all of these when the reaction gets to equilibrium. Okay, so the other thing I probably should have put in here is what the Ka is for this particular acid. This is usually given in these problems, and in a homework problem you would be able to look it up, but it's 1.3 times 10 to the minus 5. Okay, all right, so what we're doing here is we're going to start with the propanoic acid, HC3H5O2. We're going to have an aqueous system, so we're going to put into this solution initially 0.100 molar solution. This solution is going to dissociate into ions, breaking up into hydrogen ions that are aqueous and into the propanate polyatomic ion, which is going to have a -1 charge. So this is a monoprotic acid. These start at 0 and 0, so we don't have any of these initially, but as the change occurs and it shifts to this side, we will get some ions in solution. So this is going to go down by x, this will go up by x, and according to Le Chatelier's principle, since these are 0, the reaction will proceed in that, the direction to the right. And then we're going to reach equilibrium. So I'll throw the arrows in here for equilibrium, and what we end up with is at equilibrium 0.100 molar minus x, 0 plus x gives me x, 0 plus x gives me x. And now I'm ready to solve. Okay, what I'm looking for is what is the concentration of the propanoic acid at equilibrium, what's the hydrogen concentration, the hydrogen ion concentration at equilibrium, and what's the propanate ion at equilibrium. Okay, so let's go ahead and do those calculations. So I'm going to use is Ka. My Ka is equal to the hydrogen concentration, okay, times, so there's the expression. Take the time to write this step out. I know a lot of you will skip this, but especially since we have a very typical pattern for these problems, especially the weak acid and weak base problems, we always get x squared on the top and 0.100 molar minus x on the bottom. Okay. Now keep in mind that when we're doing this, we are going to drop this portion out. This drops out because our Ka is so small, the reaction doesn't shift very far to the right, so this change compared to 0.1 is very small and can pretty much be ignored for most of the problem. Okay, so I'm going to set this equal to 1.3 times 10 to the minus 5th, and now it's just a matter of solving for x, and I think you guys can do that at this point. Now keep in mind what x is equal to. X is equal to the hydrogen concentration and the propanate at our equilibrium point. So that's exactly what we want. Hydrogen concentration equal to our propanate, which is C3H5O2 minus. So when you solve for x, which I'm assuming you guys can do, I'm going to end up with 1.14 times 10 to the minus 3rd molar. Okay, so that's the answer to the first question that I have. What's the concentration of the species? Now, this is just the concentration of the hydrogen ion and the propanate. What is the concentration of the C3O, the acid? It's going to be 0.100 molar. It stays the same essentially. Now, if you want to, you can come subtract this out and figure out what that difference is, but it's such a small amount we can kind of ignore it. Okay? So now what I'll do is I'll show you the calculation for the pH. Okay, so if I'm going to calculate the concentration of pH, okay, what I need to know is what my concentration of the hydrogen ion is, and I already figured that out, 1.14 times 10 to the minus 3rd molar. So I can right away predict roughly what that pH is going to be because your pH is closely tied to the exponent. Okay, so I know that my pH is going to be 2 point something something something. Okay, like based on the fact that it's the log. Remember, pH is the negative log of the hydrogen concentration. What a log is the power of 10, right? So I know that it's going to be close to that, 3. So if I plug this in to my calculation and I hit the equal button on my calculator, I get 2.943. Okay, they get more numbers, but I'm going to stop there because of significant figures. And if you remember, with significant figures, we start counting after the decimal. So 3 significant figures. We do not count this one. So no counting of the significant figures on that first number here, that ones place. Okay, so there's my pH. My pH is 2.94. Okay, 43. I can't write this. We'll try that again. Whatever. Okay, close enough. All right, the last part, which is the percent dissociation. All right, percent dissociation, we want to look at how far to the right does the reaction go. Dissociation is the amount, how much it shifts or how much it breaks up into ions. So how far to the right does the reaction proceed? Well, since we know that Ka is small, this should be a very low number. So we're going to take our change in x and compare it to our initial concentration that we started with and multiply that by 100. Okay, so we're just going to take and plug in. We get the 1.14 times 10 to the minus third, okay, molar, over 0.100 molar. So our molarities cancel out. Multiply that by 100 to turn it into a percentage, and you end up with 1.14% dissociation. That is a pretty bad dissociation. It's very low. So what that tells us is if we were to look at a solution of this propanoic acid, how would we expect it to see? We would see it as a molecule. We would not ionize this. We don't really get many ions in this at all, so we keep it together as a group. As opposed to something like HCl, which ionizes almost 100%, we would write that as H plus, Cl minus. Again, that goes back to predicting products. Okay, that's the end of this video. Hope you guys enjoyed it. I will see you later.